Hello everyone. In the last video we have learned different types of relations, and in this video we are going to learn an important property of equivalence relation, and then we will learn equivalence classes and how to find equivalence classes. This is an important topic, but very few talk about this topic. But after watching this video you will learn how to find equivalence classes very easily, and you can understand the concept of equivalence classes very clearly. So watch this video thoroughly to understand all the concepts of equivalence classes. So let's start. An important property of equivalence relations. What is the important property of equivalence relations? We will learn now. If relation R is an equivalence relation on a set A, then it decomposes set A into pairwise disjoint subsets. All elements of a subset are related to one another under the relation R, and no element of a subset is related to an element in any other subset. This is an important property of equivalence relation. For example, to understand this property, we take an example. Let set A is equal to the set of all integers, and the given relation R is all ordered pair x and y such that x and y belong to the set of integer and x minus y is an even integer. This is the relation x minus y is an even integer. Now try to understand. Here we see that relation R is reflexive, as x is related to x for all x belongs to the set of all integers, as x minus x is equal to 0, and we know that 0 is an even integer. That's why x is related to x, hence this relation is reflexive relation. And this relation is also symmetric relation, as x is related to y implies that y is related to x. As x is related to y implies x minus y is even, implies y minus x is also even. Hence we can say that this relation is symmetric relation. And also this relation is transitive relation, as x is related to y and y is related to z implies x is related to z. As x is related to y and y is related to z implies x minus y is even integer, and y minus z is also even integer, implies x minus y plus y minus z is even, implies that x minus z is even, implies x is related to z. Hence x is related to y and y is related to z implies x is related to z. Hence we can say that this relation is transitive also, because this relation is symmetric, reflexive and transitive. Hence this relation is an equivalence relation. Thus we can say that R is an equivalence relation on set A, which is equals to the set of all integers. Now consider the sets A1 and A2, where set A1 is the set of odd integers and set A2 is the set of all even integers. Thus we observe that intersection of A1 and A2 equals to 5 implies that intersection of A1 and A2 an empty set. Hence we can say that set A1 and set A2 are disjoint sets. And we also observe that union of set A1 and set A2 equals to set A itself, which is equal to the set of all integers. And we also observe that if x and y are any two elements in set A1, then x is related to y. And if x and y belongs to set A2, then x is related to y. But no element in set A1 is related to any element in set A2. For example, if x belongs to set A1 and y belongs to set A2, then x is not related to y. Let's take another example. Let the element of set A are A, B and C, and all the ordered pairs of the relation are AA, AB, BA, BB, CC. These are the ordered pairs of the relation which is given. And it is also given that this relation is an equivalence relation. Suppose we have two sets A1 and A2, and the elements of set A1 are A and B, and C is the element of set A2. Now we see that intersection of A1 and A2 is equal to phi, implies that set A1 and A2 are disjoint sets. Also we see that union of A1 and A2 is equal to set A itself, and we see that elements A and B belong to set A1, and A is related to A and A is related to B. Also we see that C belongs to the set A2 and C is related to C. Here we see that A is not related to C and B is not related to C, because A is the element of set A1. A is the element of set A1, and the element of set A1 is not related to the element of set A2. And also we see that B is an element of set A1, and we see that the element of set A1 is not related to the element of set A2. So here we see these facts about equivalence relation, which is an important property of an equivalence relation. Now we try to understand equivalence classes. Let A be any non-empty set and R be an equivalence relation on set A. Again, let A1, A2, A3 and up to AK be mutually disjoint subsets of set A such that union of AI equals to set A. Every two elements in any AI are related to each other. If X belongs to AI and Y belongs to AJ, then X must not be related to Y if I is not equal to J. For example, to understand this explanation of equivalence classes, we take an example. A1 refers to AI and A2 refers to AJ, where the elements of A1 are A and B and the elements of A2 is C, and all the ordered pairs of the relation are AA, AB, BA, BB, CC. These are the ordered pairs of the relation R. Now we know that relation R is an equivalence relation on set A, where the elements of set A are A, B and C. But why this relation is an equivalence relation? This relation is an equivalence relation because this relation is reflexive. But why this relation is reflexive? This relation is reflexive because every element of set A is related to itself. Here we can see that A is related to A in the ordered pair of the relation R. We see that A is related to A. Again, B element which belongs to set A, and we see that B is related to B, and element C belongs to set A, and we see that C is related to C. Hence we can say that this relation is a reflexive relation. Again, we see that this relation is symmetric relation. Why this relation is symmetric relation? Because A is related to B and B is also related to A. Hence we can say that this relation is a symmetric relation. Now we see that A belongs to B and B belongs to A and A belongs to A. Now understand again. Suppose A is X and B is Y, and we see that now X is related to Y and Y is related to Z, and X is again related to Z. Hence we can say that this relation is a transitive relation, because this relation is reflexive, symmetric and transitive. Hence we can say that this relation is an equivalence relation. Now we see that elements A and B belong to set A1. Suppose A1 is AI and element C belong to set A2. Suppose A2 is equal to AZ. Now suppose X refers to A and B and C is Y, then A is not related to C, implies X is not related to Y, and B is not related to C because B is X. So we can say that X is not related to Y. Hence here the subsets which is given in this explanation of equivalence classes, A1, A2, A3 and up to AK are called equivalence classes. These subsets are called equivalence classes. And in the example, equivalence class of A equals to set A1 and equivalence class of element C equals to set A2. Now you can see that if we find the union of A1 and A2, then we get set A itself. And if we try to find the intersection of A1 and A2, then the intersection of A1 and A2 is phi. It means we can say that subsets A1 and A2, which are the subsets of set A, are mutually disjoint subsets. And again we see that element which belongs to set A1 is not related to the element which belongs to set A2. Again, the element B which belongs to set A1 is not related to the element which belongs to set A2. So here the conditions first, second and third. But second condition says that every two elements in any AI are related to each other. So any AI means A1 may be AI or A2 may also be AI. So in A1 we see that elements A belongs to A1 and B belongs to A1, and because here it says that every two elements in any AI are related to each other, and here we see that A is related to B in the relation. In the relation we can see clearly A is related to B, and C is the element of set A2, and in the relation we see that C is related to C. So this statement is also true, because here we can see clearly that every two elements in any AI are related to each other. Here we can see that A is related to B and C is also related to C. So this statement is also true. Now all the conditions is satisfied. Condition 1, union of all subsets of set A is equal to set A itself, and every two elements in any AI are related to each other, and if X belongs to AI and Y belongs to AJ, then X is not related to Y if I is not equal to J. So what does mean I is not equal to J? Here I is not equal to J means if I is 1, then J must not be 1. If I is 2, then J must not be 2. If I is 1 and J is also 1, then X belongs to set A1 and Y also belongs to set A1. It means X and Y both are the elements of set A1. So in that case, it denotes only one set. That's why it is written I is not equal to J. Now try to understand definition of equivalence classes. What is the definition of equivalence classes? If R is an equivalence relation on a non-empty set A and X belongs to set A, the equivalence class of X denoted by X inside the big bracket is the set of those elements from which are related to X. Now equivalence class of X is written like this. Here we write X inside the big bracket and we read equivalence class of X equals to the set of all Y belongs to set A such that Y is related to X. Now if we want to find the equivalence class of X, then X must be at second place in the ordered pairs in the relation R, and the set in which first elements of the ordered pairs are taken and the first element is related to the second element and second element is that element whose equivalence class is being found represents the equivalence class of X. Remember, if X1 and X2 belongs to set A, then either equivalence class of X1 is equal to equivalence class of X2, or intersection of equivalence class of X1 and equivalence class of X2 equals to phi implies that equivalence class of X1 and equivalence class of X2 are mutually disjoint subsets. Any two equivalence classes implies that any two equivalence classes are either identical or disjoint. Thus, an equivalence relation R on a non-empty set A into mutually disjoint equivalence classes. Now we try to understand some important facts for equivalence classes. First is, if we want to find equivalence classes, then the relation R must be an equivalence relation. And second, any two equivalence classes, say equivalence class of X1 and equivalence class of X2, are either identical or disjoint, implies equivalence class of X1 is equal to equivalence class of X2. It means equivalence classes X1 and X2 are identical, or intersection of equivalence class of X1 and equivalence class of X2 is equal to phi. It means equivalence classes X1 and X2 are disjoint sets. Every two elements in set AI are related to each other. And fourth is, if X belongs to set AI and Y belongs to set AJ, then X is not related to Y if I is not equal to J. And fifth is union of AI, where I belongs to set of natural numbers and the smallest I is 1. And here AI indicates that A1, A2, A3 and up to AK. And we say that union of AI is equal to set A. It means union of A1, A2, A3, A4 and up to AK is equal to set A itself. Now try to understand these important facts for equivalence classes with the help of an example. Let the element of set A are 1, 2 and 3, and all the ordered pairs of the relation which is given are 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. And this relation R is an equivalence relation. Why this relation R is equivalence relation? This relation R is equivalence relation because this relation is reflexive, symmetric and also transitive. Hence we can say that this relation is an equivalence relation. How we can say that this relation is reflexive, symmetric and transitive? Let's try to understand. Relation R is reflexive as 1 is related to 1, 2 is related to 2 and 3 is also related to 3. Relation R is symmetric as 1 is related to 2 and 2 is also related to 1. Relation R is transitive as 1 is related to 2 and 2 is related to 1 and 1 is also related to 1. Here suppose 1 is X and 2 is Y and 1 is also Z. Then we can say that X is related to Y and Y is related to Z. Implies that X is related to Z. Hence we can say that this relation is transitive. Because this relation is reflexive, symmetric and transitive, hence we can say that this relation is an equivalence relation. Now we try to find equivalence class of 1, equivalence class of 2 and equivalence class of 3. Here the equivalence class of 1 is equal to the set of all Y belongs to set A such that Y is related to 1. In other way we can say that the set of all Y belongs to set A such that all ordered pair Y and 1 belongs to the relation. Here we want to find the equivalence class of 1. That's why 1 should be at second place in the ordered pairs which belong to relation R. And we see that Y is related to 1 implies Y is 1 because 1 is related to 1. Also Y is 2 because 2 is related to 1. It means elements 1 and 2 are Y. It means the set whose elements are 1 and 2 is equal to the equivalence class of 1. Now equivalence class of 2 is equal to the set of all Y belongs to set A such that Y is related to 2. In other way we can say that set of all Y belongs to set A such that all ordered pair Y and 2 belongs to the relation R. It means Y should be at first place and Y should be related to 2 and 2 is at the second place in the ordered pairs which belong to set of relation R. So we can see that 1 is related to 2 and 2 is also related to 2. So elements 1 and 2 are Y. Hence, the set whose elements are 1 and 2 is the set which represents the equivalence class of 2. Now we find equivalence class of 3. So equivalence class of 3 is equal to the set of all y belongs to set A such that y is related to 3. In other way, we can say that the set of all y belongs to set A such that all ordered pair y and 3 belongs to the relation R. Here we want to find the equivalence class of 3. It means 3 must be at second place in the ordered pairs, and we see that 3 is related to 3 and 3 is at first place in the ordered pair, and this 3 is related to that 3 which is at the second place in the ordered pair. Hence, we can say that this 3 is y. Because this 3 is y, it means element 3 is the element of that set which represents the equivalence class of 3. So here we observe that R is an equivalence relation because R is reflexive, symmetric and transitive. And second point, which is given in this rule, any two equivalence classes, say equivalence classes of x1 and x2, are either identical or disjoint. So here we see equivalence classes 1 and 2 are identical. It means equivalence classes 1 and 2 are equal. And also we see that intersection of equivalence classes of 1 and 3 is equal to 5. Again we see that intersection of equivalence class of 2 and equivalence class of 3 is equal to 5. It means equivalence class of 2 and equivalence class of 3 are disjoint sets. Here rule 3, every two elements in AI are related to each other. Here AI represents A1, A2, A3. These are AI, where equivalence class of 1 is equal to set A1 and equivalence class of 2 is equal to set A2 and equivalence class of 3 is equal to set A3. And also set A1 is equal to set A2 whose elements are 1 and 2, and the element of set A3 is 3. Now we see that 1 is related to 1 and 3 is related to 3. Now try to understand fourth rule. Fourth rule is if x belongs to set AI and y belongs to set AJ, then x is not related to y if I is not equal to j. So here in fourth rule you can see that elements 1 and 2 belong to set A1 which is equal to set A2. It means elements 1 and 2 belong to set A2 also, and element 3 belongs to set A3. Then 1 is not related to 3 because 1 belongs to A1 but 3 belongs to A3. Also 2 is not related to 3 because 2 belongs to set A1 but 3 belongs to set A3. Again we can say that 1 belongs to A2 and 3 belongs to A3. It means element of one equivalence class is not related to element of other equivalence class. Again 2 belongs to set A2 and 3 belongs to set A3. So we can say that element of one equivalence class is not related to element of other equivalence class. Here Equivalence classes which are identical or equal considered the same equivalence class. So equivalence class 3 and equivalence class 1 are different, or equivalence class 3 and equivalence class of 2 are different. I hope you have understood all the concepts related to equivalence classes, and I am sure that you are able to find equivalence classes very easily. So thanks a lot for watching this video, and if you have not subscribed the channel MathsHiMaths, then please subscribe this channel and also subscribe AR Study Circle for getting the knowledge of English. Thanks again. Thanks a lot for watching this video.